Okay, so we're going to go through the derivation for van der Waals equation. And one of the students asked me, how do you do this? So this is really the answer to the question. So let there be a force of attraction, and we could now compute the force of attraction mathematically. This is a little complicated, so we want to spend a bit of time on this carefully. And so let's assume that in a gas sample you have two volume elements, V1 and V2. Okay, and there's some particles in this volume and some particles in the other volume. If there is force of attraction between the two entities, then depends on the distance of separation and the number of particles between the two of them. Okay, so now if you take this two volume elements, and if you double the number of particles in one of these elements, then the force of attraction doubles, because you have twice the number of particles in V1, then the force exerted on the particles in V2 will be twice as much. Similarly, if I double the number of particles in V2, it also doubles the force of attraction between the two volume elements. So because of that, so the number of particles in a volume, so it is concentration. So the force will be proportional to c squared. Okay, this is the key argument. Once we get past this argument, everything is very, very easy to do van der Waals equation. So this is the trickiest part that he figured out. Now the force of attraction will be proportional to square of the concentration. And square the concentration because the number of particles in one volume control the attraction on the other, and the number of particles on this control the attraction on that. But we are calculating the net force of attraction. So it multiplies. So C1 times C2. So if you increase the number of particles here, the attraction increases. If you increase the number of particles here, also the attraction increases. So it depends on twice one multiplied by the other, not sum. That's the key difference to figure out. It's the product and not the sum. And so C squared, concentration squared. And because concentration 1 and concentration 2 are one and the same, because gases have uniform concentration throughout the volume. So C1 equals to C2, and therefore the force of attraction will be proportional to C squared. C squared, this concentration squared, is the number of particles squared divided by the molar volume. So V bar. So this is generally how we write molar volume. Excuse me, that's not correct. So that is 1 over V bar squared. Not that's not V bar, that's V. So N over V, 1 over V bar squared. So correction for the pressure term will be equal to some proportionality constant divided by V squared. That's the key. This V is V bar squared. Okay. Too many corrections on this slide. Somehow it missed me. Anyway, so but the key part to again remember is that the actual pressure, okay, that is the ideal pressure, should be equal to the actual pressure that measured in the lab plus this correction term. So remember we said, ideal pressure is larger than the gas pressure if the particles are attracting each other. Now we say that particles attract each other because you can condense them into a liquid. And so the fact that you can form a liquid means the attractive forces are, forces are attractive in nature. And therefore we measuring pressure that is less than ideal pressure. And so the correction is B plus some constant divided by V bar squared. And so that will be ideal pressure. So in PV equals 10 RT, ideal gas, we're going to write this for the pressure term. Okay, so that's pressure correction. The volume correction next, and this is very easy. We already looked at it in sufficient detail. Since gases can be condensed into liquids, volume available for each molecule is less than the volume of the container. So for example, you start with an empty container and you put a particle, the first particle. The first particle can occupy the entire volume of the container, right? So it can go here, there, and so on and so forth. But if you introduce a second particle, then that second particle cannot occupy the entire volume because part of the volume is occupied with the first particle. So total volume V minus the volume of the first particle. That's the volume available for the second particle. And similarly, third particle, fourth particle, as you have more and more particles into the system, less and less volume is available. So it's like a classroom, you have chairs filled. And so first student can choose any chair in the classroom, no problem. But the second student doesn't have that opportunity. They have to choose whatever is remaining. One chair is occupied, so you have the remaining chairs, only that one of those remaining ones can be occupied. The third has less and less, and so on and so forth. So till when the class is full, then the next student doesn't have a chair to occupy. So this is how it works, right? So same with molecules and containers. So the volume occupied is less than the actual volume of the container. So this is a very important deduction. And so as you can see in the early phase of kinetic theory of gases, people start understanding molecular behavior. So once the molecular behavior is introduced and you start understanding molecules and atoms forming the gas, then you can argue all these things, volume available and the pressure exerted, and you can start making correction terms. So this is why kinetic theory of gases is really important, and it connects all these things together. And so we can say the correction for volume will be some constant subtracted from the measured volume. So if you have 1 liter is the volume you measure, or say V bar for 1 mole of gas. So everything in case of van der Waals, we start using molar volume and so molar properties, etc. V bar measured value minus some constant equals to the ideal gas volume, molar volume. So B is so it's interesting that how van der Waals used A and B as constants. He didn't use V or a D or a W as constants using his initials. It's kind of interesting how you simply use A and B as the first and second constants, right? And they're stuck since then. So now you can write the ideal gas equation as the pressure correction, P plus A over V bar squared. So now everything's correct in this slide. V bar minus B, so that's correction for volume. We're subtracting the correction term, we're adding the correction term here on the pressure, and it goes to RT. This is van der Waals equation, fetches the Nobel Prize. Okay, so you should read the Nobel lecture. It's really interesting how the guy has done this beautiful work. So it's a beautiful piece of work. But one comment to make is that if you now rearrange, you have V bar squared in the denominator here and V bar here. And if you rearrange this, and you get a cubic equation, V bar cubed. Okay, so in other words, if I multiply by V bar cubed, then I can simplify these equations. I end up with a cubic equation. Minus B RT over P, V bar squared, plus A over B V bar, minus AB over P equals to 0. So people generally don't write this in the cubic form because it's hard to remember, right? But this is easy to remember because you can, by pencil, using a pencil, you can derive this in 2 minutes, in less than 2 minutes. Once we understood correction term for the volume and correction term for the pressure, we can simply write it out right then and there. So that's how I recommend you do it. Don't memorize it, but derive it. And more you derive, faster you can derive it. And the real test is if you can derive an equation or not. When you wake up in the middle of the night, you can derive it. Then you know you really mastered it. And it will come through. You just practice, that's all, just to practice. And so, but don't memorize them, never memorize. And ask questions, how is the volume done, correction done? How is the pressure done, and correction done? Why is the square term and all that stuff? Once you get that hang of it, then you will just do it just like that and no issues. So now let's look at van der Waals isotherm. And van der Waals isotherm is a cubic, right? So now I said it's a cubic. And so it looks like this. It's actually simplified. The plateau doesn't exist, but it goes like this and then goes up and then goes down and then goes back down like that. So this is a nice cubic. And so I have this is, I've exaggerated this, okay? I've exaggerated this. It's not as tall here and as not as deep as here, just to show that. And the interesting part is that these inflection points you see, and I mean, these are not done properly, but if you do smooth curves, they're not smooth curves, then you see inflection points very nicely here and here. That inflection point is where the vapor begins to condense into a liquid. You know, the rain is falling, right, in the sky today. So that's that point. And here there is no more gas left. All the gas has been consumed, and what you have now is only the liquid. So this is the pressure, and this is the volume. So you're compressing it. As you start with the gas and then compress, 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 it begins to form a liquid, and you have liquid vapor equilibrium. L/V means that it's the equilibrium between liquid and vapor. And then as you compress more and more and more, all the gas disappears. You have a pure liquid state. And the pressure rises very, very fast with volume once you have a liquid, because it's very difficult to compress a liquid. So the pressure rises very, very fast. The gradient here is larger than compared to the gradient here. Here it is like Boyle's law feature, but this is not Boyle's law feature. It's different for liquids. Normally we derive the equation of state for liquids and solids, but that's not necessary for us. You know, we don't need that for kinetics. So I cut that off. We don't need that, unnecessary for us. But you can study. You can read how to describe this mathematically, and we can actually do that quite nicely these days. It's I think chapter 7 maybe in the book, or chapter 6. Very detailed description of equation of state for condensed phases given there. And so now, so those are the things. And if you're curious, we can ask, what is really A and what is really B, etc. Now, since A depends on the interaction terms, and I've given you values of A for different gases: helium, hydrogen, nitrogen, oxygen, methane, carbon dioxide. As A depends on the interaction term, the value increasing means that the interactions are getting stronger and stronger. Okay, so if the value of A is 0, for example, then an ideal gas, right? So because no pressure correction applied, maybe only volume correction required. And if B equals to 0, then no volume correction required, only pressure correction maybe. Both are 0, then it's an ideal gas. So, but a value of A goes higher and higher and higher, means that you have to add more and more to the measured pressure. And therefore that means it has stronger attractive forces. And this is realized in the lab, because easy to condense CO2, pretty easy. Applying pressure, you can make CO2 in the solid form very quickly, very easily. And on the other hand, the liquefaction of helium is very, very hard. You have to go to very low temperatures to do so. So the value of A gives us how easy it is, or how difficult it is to form a liquid from a gas. So in other words, proportional to intermolecular forces. And so then as a physical chemist, you say, well, if A is related to intermolecular forces, and it should also be related to the boiling points of the liquids. Because if the intermolecular forces in the liquid state, not in the gas state, but liquid state, are stronger, then the liquid will boil at a higher temperature. Right? So that's the idea. Because when you take a molecule from the liquid phase and put it in the gas phase, you have to do work. So that work requires doing work against the forces of attraction in the liquid. And so that is proportional to the temperature needed to raise, to convert the liquid to the gas phase. So one can ask, is there a correlation between the boiling points of gases and the value of A? In fact, I will let you do this, and you won't be the first one to do this, but you'll have checked this already, and you will learn something very interesting, okay? Yeah, it is proportional too, but it's not the way you thought it would be, and you will see that. And in a similar way, the B is a correction term for the volume. And so you can ask, B might correlate with the density of the solid, for example, or the liquid. And so take the densities of these liquids and then plot if B is any correlation with it. Again, you learn something really interesting from that as well. So we don't have time for those but you can certainly do those.